Number 24. A sample of solid potassium nitrate is placed in water. Look at that, they're doing it right there. The solid potassium nitrate comes to equilibrium with its dissolved ions by an endothermic process. Ooh, that's important information. And nicely, they put the energy in for us so we don't have to remember that endothermic is on the left. Which of the following changes to the system would increase the concentration of K plus ions at equilibrium? So, if we're going to increase the concentration of K plus ions, the reaction is going to have to shift to the right. So let's see which one of these will shift it to the right. So A, the volume of the solution is increased. That is oddly weird and vague language. So the volume of the solution is increased. Now I think what they mean by that is that you're adding more water to the solution. So imagine that we've got this beaker over here and we've got some water in there, and we have the potassium nitrate solid on bottom and the two ions that have dissolved are floating around on top. And if they add more water to the solution, it will, you might think it would allow that these dissolved particles to expand. But the problem is, as soon as you do that, more of the solid is going to come out and dissolve and essentially fill up that space. So in the end, the concentration isn't really going to change at all. And so while it may create more potassiums, it's not going to change the concentration of the potassiums, which is what they were asking for. So I don't think either one of these is true. As a matter of fact, the volume of the solution is decreased is sort of the reverse. If you evaporate some of the water, you might think, boy, you're going to have a lot more ions in a smaller space and it's going to increase the concentration. But some of them will start to precipitate back out onto the solid. So it doesn't seem likely that that would change the concentration either. So you think about it, essentially the ion, as many ions will that you need to fill up that sort of volume that you have, will either be released from the potassium nitrate if you get more water, or they will re-precipitate out if you have less. You can't change the concentration by doing that. So let's see, C, additional solid potassium nitrate is added to the solution. It's a little bit of a controversial one. I think the answer here is it shouldn't shift it at all because you're adding a solid. Solids do not shift things to the right because you're not increasing the concentration. If you were to write an equilibrium expression of this reaction, it would be K. It's a dissolving reaction. It's a weird one because this is completely soluble, but it would be KSP equals K plus and NO3 minus. There would be no KNO3 in it because it's a solid, so that's not going to shift it either way. Let's see what our last choice is. D, the temperature of the solution is increased. Well, if we increase the temperature of the solution, the reaction will shift to the right, and it should cause more potassium ions to dissolve. So I think D is going to be our best answer here. 25. A 1 molar solution of, I guess that's antimony chloride, in an organic solvent shows no noticeable reactivity. The sample is heated to 200 and the following equilibrium reaction occurs. The value of KEQ at 200 was measured to be 10 to the minus 6th. Boy, that does not proceed very well, does it? The reaction was then heated to 350 degrees and the equilibrium concentration of chlorine was found to be 0.1. Which of the following best approximated the value of KEQ at 350? So we know the value of KEQ at 200, and we don't know it at 350. Alright, so this is an equilibrium problem that looks like it might be a little bit challenging. So whenever we're stumped about equilibrium problems, we're going to need two things. One of them is right here, an ice table. And the second one we need is an equilibrium expression. Now, one of the things that concerns me a little bit is there are no state symbols on this, and I'm worried that there might be something that gets left out of the equilibrium expression. But they say that this stuff is a 1 molar solution, so it's clearly aqueous. Chlorine is usually a gas, so my only doubt is about that one. And without any other evidence, I'm going to assume that it's not a solid. Alright, so there's my equilibrium expression, and so now I'm going to fill in my ice table. Well, we knew that this was 1 molar in the beginning, and since we're trying to figure out KQ at 350, if I knew the equilibrium concentrations of these three things, I could calculate KQ. And at 350, they found that at equilibrium we had 0.1 molar chlorine. So let's assume we had 0 of these at the start. So that means this one increased by 0.1 molar, and this one increased by 0.1 molar, and the last one decreased by 0.1 molar. So that's going to be like 0.9 molar. Now, this is a pretty small difference between these. We may have to do an approximation here. So this is going to be 0.1, 0.1, and that's divided by 0.9. So let's do the 0.1 times 0.1 on top. 0.1 times 0.1 is 0.01. You can do it either by the decimal shifting method or by multiplying 1 times 10 to the minus first with itself again, and you get 1 times 10 to the minus second. Then we got to divide that by 0.9. Well, 0.9 is pretty darn close to 1, and they did say approximated. So I think the closest it's going to be is probably D. Alright, 26, we've got a reaction. They say the reaction above came to equilibrium at this temperature. At equilibrium, the partial pressure, oh, that's nice. The equilibrium partial pressure of NOBr was 4 atmospheres, not the initial. The partial pressure due to NO was 4, and the partial pressure due to bromine was 2. Look at that. They gave us all the equilibrium partial pressures. I don't even think we're going to need an ice table here. What is the equilibrium constant Kp for this reaction? Doesn't it seem like we should just plug it in? You know what we should do? Since it's a Kp, we should practice writing the Kp expression. You know, it's a little different format. See if you can do it. I'll wait for you. Pause the video. Alright, is that what you got? Well, let's check and double check our answer. I put everything in here. I'm making sure there's no solids because I don't want to mess that up. And I squared that one. That one's 1. And that one's squared. I used big P's, no brackets because it's a Kp. So that's what it should look like. Let's plug in our values. Alright, they're plugged in. Now we can do our calculation. Let's see. 4 squared on top up here. 4 squared is 16. And then I got to do times 2. On bottom, 4 squared is 16. Boy, those seem like they cancel. Is the answer 2? It might be. Yeah, I think it's D. You know what they were checking in that one? They were checking to see if we drew out the expression and if we caught that it was squared. Because if we didn't do that, we wouldn't have noticed that. Number 27. We've got a reaction. They tell us that 150, the equilibrium constant is 300. The reaction is allowed to reach equilibrium, and let's see, the partial pressure at equilibrium of IBr is 3 atmospheres. Which of the following could be the partial pressures due to bromine and iodine? Well, let's think it through with an equilibrium expression and potentially an ice table. Hey, you know, I was about to write an equilibrium expression. I didn't know whether I should write a Kc or Kp. That I'm having troubles reading a little bit. But based on this evidence, what do you think is most appropriate? I think it's a Kp. I mean, they're atmospheres. But that sure does look like a Kc that they drew. Anyway, let's do a Kp. So I've got an equilibrium expression on top. I'm doing a Kp. And I've got an ice table that I'm in the process of making down here in the corner. And so, you know, one of the things that's a little bit confusing is they didn't tell you where you started. Did you start with the reactants being 0 or the products being 0? But the one thing we do know, let's say that it's going to the right. The one thing we do know is this would increase by x, decrease by 2x. And so whatever the change is going to be based on those values, x, and 2x. Now the problem is they could be going the other way. It could be, you know, plus 2x and minus x on the reactant side. Now the other thing I'm contemplating is, does the bromine and the iodine have to be the same? And, you know, if you started with these and you were actually making it go backwards, then they would always have to be the same. But they never really said that. They, you know, you could have had way more of this than you had of that, and it went this way. So I don't think they have to be the same. All we know is if we were to take these values and plug them in here and there, and we had the 3 atmospheres up there, it should definitely come out to be the Kp, which is about 300. I'm tempted to just plug in numbers here. So I've got the general expression, and we know that 3 squared is 9. That was the equilibrium pressure of IBR. And so we've got some numbers down here, and I'm tempted to go x and y because they may not be the same. So let's see in A, if this is 0.1 and this is 0.3, let's see if that works out. 0.1 times 0.3 is 0.03. And then we'd have to do 9 divided by 0.03 and see if that turns out to be 300. Now we could do it by scientific notation. Let's see, I'm going to write it over here. 9 times 10 to the, well, I didn't move it anywhere, so I'm going to do 0. And 3 times 10 to the, we moved it, I guess it would be right there, so 2 places. But it'd be minus 2. 9 divided by 3 is 3. And then we got to subtract them. 0 minus a minus 2 is 2. So it would be 3, 1, 2, boop, boop. Looks like it's 300. So maybe A is the answer. Number 28. Initially, that's important, initially we have a hydrogen partial pressure of 6 atmospheres. It's an equilibrium problem, so we're going to do an ice table. We can do atmospheres, it's no problem, either that or concentration. We should check, by the way, all of these are gases, so I don't have to worry about any of them not being in my equilibrium expression afterwards. So in any case, hydrogen with a partial pressure of 6 atmospheres and CO2 with a partial pressure of 4 atmospheres are put in there initially, then they're allowed to come to equilibrium. The reaction above was allowed to come to equilibrium at 700 K. At equilibrium, the partial pressure due to CO2 was 2 atmospheres. Or to CO. So we're going to assume we're going to start with 0, and this one at equilibrium is 2 atmospheres. So that's going to increase by 2 atmospheres. That's going to, increase by 2 atmospheres to 2. This is going to decrease by 2 atmospheres to 2. And this is going to decrease by 2 atmospheres to 4 atmospheres. Alright, so we have all of our equilibrium values. They want to know what the equilibrium constant is. That's easy. Let's plug it in. Alright, so there we go, equilibrium expression, plugged them in, and so our Kp is going to equal, well, on top 2 times 2 is 4, on bottom 2 times 4 is 8. It looks like it's going to be roughly a half, so the answer should be D. 29. What is the volume of 0.05 molar HCl that is required to neutralize 50 milliliters of 0.1 molar magnesium hydroxide? So this is not an equilibrium one. This is pretty much a titration one. And you remember, titration doesn't matter whether they're strong or weak, but there is a trick to this one. And while we are probably going to use MAVA in its acid-base format, because it's simply a ratio, we have to be very careful here. Because even though the concentration of the acid is pretty obvious, and why don't we put that in right now, it's 0.05 molar. They want to know the volume of the acid. The concentration of the base, the magnesium hydroxide, is not 0.1. Any guesses why not? Well, it dissociates 2 hydroxides for each one molecule. So the concentration we're going to use for it is 0.2 molar. Ooh, that was tricky. And it looks like they use 50 milliliters of it. We can keep it in milliliters, but if we do, we got to remember that our answer for VA is going to come out in milliliters. So 0.2, 50, divided by 0.05. Oh dear, we get to use our math without a calculator skills again. Well, we could do it any number of ways here. We could either multiply first, or we could divide first. Let's see. Well, let's multiply first. You could do it either way. Let's do the scientific notation way. 2 times 10 to the minus first, I think, is the same as this number. We're multiplying it times 5 well, let's just leave it as 5 times 10 to the first. And that is going to be 5 times 2 is 10. And then we got to add the exponents. Minus 1 plus 1 is 0, so that's really just 10. So our top is just 10, our bottom is 0.05. And you might be able to decimal push at this point, but if not, we could go back to calling 10 we could go back to calling 10 times 10 to the 0 like we originally had it, and call this 5 times 10 to the minus 2. 10 divided by 5 is 2, and then we got to subtract exponents. So we're doing 0 minus a minus 2, which is really like adding. And so 10 to the second. So that would come out to be, what's that? Oh, that's 10 to the first. Would it come out to be approximately 200? So is the answer B? I believe it is. Number 30, which of the following best describes the pH of a 0.01 molar solution of HBRO? Well, you know, this is one of these ones. We have seen a very similar question like this in 5 Steps to a 5. And yes, it is possible to get the answer without doing an ice table or doing any of that stuff. Let's start and at least figure out, do we need an ice table here? Because if this is a strong acid, we don't need an ice table, because that means all of it would dissociate. Well, you go through your inventory of strong acids, and no, that's not a strong one. So it's a weak one. So let's think for a second if it was strong. If it was strong, we could simply do pH equals negative log of the concentration of 0.01. And you remember, we can estimate negative logs if we change this number to scientific notation. 1 times 10 to the minus 2. And if you do that, you remember that the power will tell you what the pH would be. So this solution would have a pH that's approximately, not approximately, in this case, if it was a strong acid, it would be 2. Now, it's not a strong acid, so that tells you right away it's not going to be 2. As a matter of fact, it's not going to be lower than 2, because 1 would be even more acidic. So that's going to narrow it down pretty quickly. It is an acid, so you know it's not going to be the answer C, because that's neutral. It's not going to be the answer D, because that's basic. So you can tell pretty quickly that the answer is going to turn out to be B. Now, but since we're looking at this and we're really trying to learn, if we were going to figure out the pH for this, remember it's a weak acid. The proper approach would be, well, in multiple choice, the proper approach would be the rationale we just used. But if you were doing this on free response, you would want to draw the dissociation reaction of the acid. And you remember, because it's a weak acid, you can't just do this simple stuff up here. You've got to actually draw out an ice table. You would say this is 0.01 molar. You would say these are 0. This goes down by x. It'd be 0.01 minus x. These would go up by x and up by x, or it would be x. It'd go up by x, and that would be x. And then you would take these numbers. You would plug them into an equilibrium expression. You would use this Ka, which actually might be a manageable one. Let's try it out and see what happens. Our equilibrium expression would be the Ka, 2 times 10 to the minus 9th, equals x times x, which of course is going to be x squared, over 0.01 minus x. We would assume this x is really small. You know what? I know we don't need to do this, but equilibrium is just fun, so that's the reason we're doing it. And then we get to this point, we'd have to multiply 0.01 times 2 times... You know what? Math without a calculator is fun. Let's do it. Now let's see, that'd be 1 times 10 to the minus second. That'd be 2 times 1 is 2. We'd have to add the exponents. That's minus 11th. And then that would be equal to x squared, because remember we were up here and now we're down here after we did the math. And then we'd have to take the square root. Oh, well, if that was minus 12, it would be a lot easier. So we couldn't, if it was minus 12, you remember we just to cut the exponent in half, it'd be pretty easy. So they didn't set it up easily for us to do the square root thing. I mean, we could estimate it, you know, it'd be somewhere around minus 5 or minus 6 once you took the square root. So, you know, I don't know, it'd be 1 point something times 10 to the minus 5 or minus 6. When then you pH it, you get a pH around 5 or 6, and the answer would still come out to be B. Okay, lastly, a technician wishes to create a buffer that has a pH of 5. Which of the following acids would be the best choice for the buffer? Now, it's pretty easy to kind of actually pick that out. But let's go through the rationale. Can't think about buffers without the Henderson-Hasselbalch equation. Oh, I always forget. What goes on top? Is it the acid or the base? It's the base. That's right. So the base of it goes on, of the buffer goes on top, and the acid goes on bottom. Remember, a perfect buffer, as in, well, an optimal buffer, would have the same concentration of both of these. And if it's true, that'd be 1, this would go away. So the optimal buffer is going to be the situation where the pH is equal to the pKa. Well, if the pH equals 5, then the pKa is going to have to be 5. And you notice that up here they've got a lot of Ka's. Well, if the Ka is going to be pK is going to be 5, then the Ka has to be 1 times 10 to the minus 5th to get a perfectly 5 pH. You remember the power rule in the same way we do pHs works here. And so I'll let you look through those choices, but when I look through it, it looks to me like C is probably our best choice.